lecture. And today we're going to be talking about fine tuning. And there's several interesting things to go over with fine tuning. So first, I wanted to just recap. So in lecture 6, we talked about pre-training. And the basic idea with pre-training was to take some data, run the pre-training, minimize the pre-training objective, and then you get this base model. Now, we talked about different ways of that you could adapt these base models to tasks in different ways. So one way is through prompting, and this was in lecture 8. And so here the paradigm is you take a base model, you want it to perform a particular task, so you describe the task in the prompt and also provide it with some task example. You could then get the model to perform different tasks by writing different prompts. Today, we're going to talk about the other paradigm for adapting a model to tasks, which is fine-tuning. So here, and we'll go through the details, here you have some task relevant data. So let's say we want to make a translation model. Then we would collect, for example, these paired sentences of one language and another. And then we'll apply this fine-tuning procedure where we again minimize some loss, and we'll see it in a bit. And then that gives you a model which is specialized for the task. We'll also talk about this kind of trick you can do, which is you can train a model to just perform multiple tasks. So that'll be called instruction tuning, and you'll get what's called an instruction following model, which you can instruct it to do many different tasks. So kind of clever trick that we'll see. And so today we'll go over 4 different things. As with many of these lectures, it is my first time giving them, but I think we should be able to get through all of them in today's lecture. Again, we're just going over the kind of basics of them so that you've seen them. And all of these ideas are very relevant to, you know, NLP today, as well as potentially your projects. So hopefully you learn a lot of useful things today. So in particular, I'll go over the basics of fine tuning. I'll go over instruction tuning. I'll briefly introduce ideas for what's called knowledge distillation and talk about how it relates to things like instruction tuning. And then briefly at the end, I'll talk about one of the main methods for doing efficient fine tuning. You'll actually see this in a lot of different fine tuning code bases nowadays, and you might even use it a lot in practice if you don't have a lot of computational resources like multiple GPUs. Okay, so first I'm going to go through standard language model fine-tuning and talk about some of the effects of fine-tuning, why you would want to do it. So in standard language model fine-tuning, the idea is we start with this pre-trained model. We'll denote it as p theta of y given x. And now we collect a data set. And suppose our data set has both inputs and outputs. So the inputs will be x and the outputs will be y. And now we optimize the following loss, and you probably recognize it. It's essentially the same loss that we use for pre-training. We now use it for fine-tuning. So here it's saying that you go over your data set, and for each different example, you minimize this objective here, or you could have this as a loss function. And the objective says that the model should learn to predict the next token in the output sequence. So can anyone tell me what this objective is called, or what this optimization is called? Yeah, exactly. So it's called maximum likelihood estimation, and then the loss function that you minimize ends up being this cross entropy loss. And so this is the same idea that we've seen now in several lectures. In lecture 3, I talked about this maximum likelihood estimation and cross entropy loss. in the context of these very simple bigram models. We also saw it come up when I was talking about the recurrent neural networks, and we talked about it in pre-training. It's the same kind of next token prediction objective that you use for pre-training. Now we're just going over our data set that we've collected and applying the next token prediction loss to the output sequences. So in summary, and we'll look at a few examples and then I'll show a code example as well to make this very concrete. But first I wanted to just stay abstract for a second. And so again, fine tuning is some procedure that takes in your pre-trained model, takes in some data, and then takes in some loss function. And in the case of language modeling, we have a pre-trained language model, we have this paired data, and we use this cross-entropy loss. So although I'll talk about language models a lot because that is the technique that's used widely in natural language processing today, the idea of fine-tuning isn't anything specific to language models. For example, you can fine-tune a BERT model, which is a masked language model. You can also use different loss functions. You don't necessarily have to use this cross-entropy loss. And you'll see fine-tuning come up in other contexts, like you could fine-tune image classification models and things like that. But aside from the slide, we'll mostly focus on language models because currently that is what's used a lot for advanced NLP. Okay, so any questions about this? And then we'll see some concrete examples. So if the question is about like concrete examples, we'll see this. Okay, so just to give a sense of some different tasks and some actual training data, one example is, let's say you want to do summarization, then your input X might be some paper, and your output might be an abstract. Pretty useful if you can do this. And you can actually go online and find data sets for this. Here's one where they collected 300,000 different examples. And then here again, you have the string of the entire paper, and then you would have the abstract, and you fine tune the model to generate the abstract given the article. Okay, and then again, in case you haven't seen this site before, or just let's just take a look at what's here. You could again look for various data sets for the tasks that you're interested in. And there's a chance that maybe someone has a data set here. And this is actually where I took the screenshot from. So yeah, that's an example. Another example is, let's say you want to do problem solving, like solve math problems. Then again, you could put it into this form where now your input X will be some string, which is the problem, and your output Y will be the solution. Okay, so there's also data sets for this. A really famous one is called, unfortunately, it's called the math data set, MATH, all capital letters. And they have a training set of 7,500 examples. So one thing you could do is you could take a language model and then fine tune it on this training data set. And then hopefully it's a bit better at solving these kinds of math problems. This is an interesting example. So this one is a bit more general in some sense. You could imagine your input X just being some type of prompt. And then the output is a response. So imagine you have a chatbot. So you could see this data set here has 2,900,000 examples. And you could see that the inputs here are kind of different. They're not necessarily like math problems or summarization. This one says, how does the sentence end? Whereas this one says, write a sentence not in English. And then you have a response here. So we'll actually talk about this later. This is kind of getting at this instruction tuning idea. But again, you can find these data sets on this website. And if you haven't seen them before, look through them to yeah, get a sense of different kinds of data that people fine tune their models on. Um, so then, yeah, there's a really simple code example I put together in the course code repository. And so basically what it does is it solves um, the usual task in this class, which is generate names. So here we again start with this name data set. And then here it's starting with this really small language model. So I actually ran this on my MacBook and did the fine tuning on my MacBook. But the idea is, yeah, now we're starting from a pre-trained model, whereas in the previous code examples, we were starting with like a transformer or RNN just from scratch. And then there's two things that I had to do here. One is you have to add in these special tokens to the vocabulary. So this one will be to do padding. So I've talked about that before. If you have variable length sequences in the batch, then you have to kind of pad the extra positions. And then this is maybe not strictly necessary, but I just added in this start of sequence token. Okay, and then since we're working with a pre-trained model, we have to actually resize the model's embedding layer so that it adds these two additional tokens. Now here, I maybe won't go through the details here, but I mean, there's not much code. Here, I'm just implementing these like PyTorch data sets and data loaders. So it's taking in the names data set. Here, it's adding in the BOS token and end of sequence token. And then this is forming a batch. And you can see here, it's like using the built-in functionality from Hugging Face to take care of the padding. So now we have different data sets and you can see what a batch looks like. So one interesting thing here is you can see some of these names are, like 4 characters long. And so when we're using the character level model, sorry, 8 characters long. So when we're using the character level model, the sequences would be longer. But now we're using a model that has been trained with the byte pair encoding. So you could see that the names are typically like 2 or 3 tokens long because now you have these subwords. Um, and then here's just like exactly how the data is formatted. So so there you go. And then the training loop is pretty similar to the ones we've been looking at, and this is all it comes down to. You loop over your training set, you get the inputs, and you have to set the attention mask. Um, and then you also give the labels. And then this is using Hugging Face, so it'll actually take care of like, at least I believe it does, of shifting the labels. And then yeah, compute the loss. Again, Hugging Face has this loss computation kind of built in, and then do the optimization. Okay, so it did take like a little bit of time to run a full epoch on the laptop, but you can get a model here, and then you can generate some names with it. So that's like a very simple fine-tuning loop. And I also put in here, oh, and yeah, you can run it yourself. I also put in here an example from the Hugging Face Transformers library. So some people actually still use the script, for like research purposes or fine-tuning purposes. And if you look at this one, the code is a lot longer. So they have a ton of different options. Um, they, yeah, they have options for also like parallelizing the model and things like that, and dealing with data sets. So there's a ton of setup code. But then ultimately, these fine-tuning scripts always have this same kind of main loop that we saw in the very simple example. So here's where it's saying, okay, I'm going to iterate over each batch in the data loader. I'm going to do the forward pass, compute the loss, and then do the back propagation. Okay, and there's a bunch of extras added in, like this can help you parallelize across like multiple devices and things like that. But ultimately, you'll see this like core training loop in part of any script. Mhm.
Professor, in the script that you showed, so essentially we are trying to train it in such a way that we predict the next token, right?
Mhm.
So how is it exactly different from pre-training? Because even in pre-training, aren't we doing the next token prediction task where input is a sentence and the target is sentence like shifted by one step?
Mhm. Yeah. Yeah, exactly. So the language models are fairly simple in the sense that you pretty much always, in standard case, use this next token prediction objective or cross entropy loss, whether you're pre-training or whether you're fine-tuning. The only difference with fine-tuning is that you start with a language model that has been pre-trained. So you start with this model that is already pretty good. And then on your smaller data set, you optimize the loss. Yep. Mhm.
Could you please go to that part in the code where you set the beginning of sentence and padding tokens?
Yeah. Oops.
Yeah, just slightly above this.
Mhm.
So just like a couple, just we go like a couple of cells down where you actually printed out. Oh, yeah, over here, this thing.
Mhm.
Why is there a padding token after the end of text?
Yeah, so this was looking at a batch. And so the idea is that some names are longer than this one. And then so when you put it into a matrix, you have to fill in the extra slots. Yeah. Mhm.
Why the
Yeah.
what the output is a sentence, is a noun sentence. How to handle the number of sequence amounts of output? How to calculate the amounts?
Say it again, if it's.
So if the output is a sentence
Mhm.
and say 10 word of sentence of the true label,
Mhm.
but the model just return eight, then how 8 word of sentence, then how to calculate it?
Oh, yeah. So at training time, what you do is you give the model, or let me actually show it in the formula and talk through it. So at training time, you take the full sequence from your data set, and then at each time step, you give the model the true prefix, and then you just have it predict the next token. And then for the next step, you give it the true prefix, plus one token and have it predict the next token. Yeah, so you don't have to worry about this potential mismatch in the lengths because you're always using just the data from the training corpus. Yeah. Mhm.
I have a question. During so our tokenizer would split a word into subwords, right, due to byte pair encoding.
Mhm.
So once the model has generated the outputs, I'm talking about the inference time.
Mhm.
How do we know when to split two consecutive tokens that could belong to one single word, and when not to split the tokens and rather assume that there is a space and those tokens are two separate words? How do we decide that?
So I guess your language model has a vocabulary and it's learned different probabilities. So you just have the model predict like what is the probable next token, or you sample from the distribution. And so let's say you have a word that is split into two different subwords. Well, after the model has generated the first subword, then as long as it's been trained, then the model should know that the probable next token is like the second part of the subword. So yeah, you don't really have to worry about that aspect of it.
So I didn't really get it. So let's say the model predicts two tokens consecutively, walk and ing.
Mhm.
How do we know whether it was it's supposed to be a single word walking, or it's supposed to be walk and ing, two separate words? Like that's
Oh, okay, yeah. Because there's also tokens corresponding to white space. So if you remember in when we talked about the tokenization, you can basically represent entire strings using Unicode or using these like UTF-8 bytes. And so that representation includes white space as well. And so white space could be its own token. It could be included in a subword. Um, and so it's handled by the use of BPE. Yeah. Mhm.
Start. Why did you add those two embeddings? Why were they necessary?
Yeah. So one is one is the padding token. And so the padding token is important if you're fine-tuning the model because you have to form these batches and the batches are of variable length. And then you want some consistent token so that you know to not apply the loss on these extra positions.
I guess my question was more like, how is it that the pre-trained model didn't have that token? Why was it necessary for us to add it manually?
Yeah. So it'll vary based on how the model was trained. Um, Here, what I did is look at the tokenizer, and there's a special location in these Hugging Faces tokenizer called pad ID. And since it wasn't set, I added in my own pad token. There might actually be one somewhere in the vocabulary. It just wasn't set in the tokenizer, so I added one in. Yeah. But during their training, they must have had um well, okay, maybe we're so during pre-training, you can have fixed length chunks of documents, and sometimes you don't even need padding for pre-training because you have these extremely long sequences and you just take chunks of them and then they're always the same length. Yeah. So sometimes the pre-trained model won't have the padding token. Yeah. Mhm. Okay, cool. And yeah, great questions. So that's that. And then yeah, so I believe in the recitation section, um, we'll go through in more detail, how to fine tune a model with the Hugging Face code. So if you're not familiar with it or you just want a refresher, there'll be a whole recitation section on this. There's also these, I'm calling them no code fine tuning libraries, where they'll have different commands like fine tune and you give it a data set in a particular format. Um, Two popular ones are called Llama Factory and Axolotl. Um, so you could take a look at these. They have a lot of different functionality. Of course, they will be very abstracted away. So if you need to, go down and do any modifications, then that gets more difficult. But if you want to do just kind of standard fine tuning, then some people find these kinds of libraries kind of useful. Um, okay, so now let me just talk about a few effects of fine tuning. Um, so one is there's this question of like, why do we use a pre-trained model in the first place? And intuitively, it seems like a good idea. Um, One like concrete thing you could say is that typically the model becomes more data efficient. So specifically here, what this is showing is if you have a model that is trained from scratch and now you're fine-tuning it on some data set, then this is showing the size of the data set that you're fine-tuning it on. You could have a data set with 100 examples, 200, 1,000, 10,000. And then this is showing the performance. And you can see that if you train from scratch, then it actually requires a lot of examples, roughly like 10,000 to reach this performance level of 10 percent, whatever that means. Whereas these two are two different strategies for pre-trained models, and you can see that this one only requires 2,000 examples, and then this one actually only requires like 130 examples to reach the same performance. I'll talk about what those are in a second. It's actually not that important because it's kind of an older paper. But then you can also see that the absolute performance that you get, given the amount of data you have, is just better. So you would have to go and collect more data to reach the performance that you get by pre-training and then fine-tuning.
Just curious, why is the semi-supervised approach better? Because they have like no labels to validate their own fine-tuning.
Yeah. So I picked this paper because this was actually before GPT, I believe. This was like one of the earliest papers to do language model fine-tuning. Sorry, pre-training plus fine-tuning. So the method, like the experiment setups are going to be a bit different than what you'd see today. But what they did, I believe, supervised is just taking the pre-trained model and fine-tuning it on the XY examples. The semi-supervised is they have the XY examples, but then they also add in additional data that's like relevant to the domain. So let's say you're doing like movie reviews, then you could have your inputs and outputs, and then also throw in a bunch of like, I don't know, movie related data. Yeah.
But that's just more data. That's it.
Yeah. So that's what it means by semi-supervised. And so this idea is kind of, yeah, I mean, it's still present in in this paradigm of pre-training and then fine-tuning. Your model kind of becomes more data efficient. So this one is a bit maybe mathematical, but I personally think it's pretty interesting. So one way you could think about this is that this fine-tuning is taking this pre-trained model, which has this really kind of general distribution over the pre-training data, and it's somehow narrowing the distribution to the data set that you're fine-tuning on. And so if you remember back to lecture 3, I talked about how the maximum likelihood objective corresponds to essentially fitting a distribution, in particular, minimizing the KL divergence between some data distribution and the distribution that your model represents. And if you remember, the data distribution is basically determined by the data set. It's viewed as a sample from data distribution. So then, as we've discussed and as people asked, we use the exact same objective for fine-tuning. So we can also think of this as fitting a distribution. So this notation just means we start with some initial model, and now we're minimizing the KL divergence between our model and our fine-tuning data distribution. So this would be represented by your fine-tuning data set. And what you can see is that like usually your pre-training data set is like trillions of tokens, from the internet. And then maybe you're just fine-tuning on like a math problem-solving data set. And so the distribution is becoming kind of narrower. And so that could be a useful way of kind of thinking about what's happening during fine-tuning. So let me talk about a few implications of this, then maybe I'll pause for questions. So like with this understanding, you can kind of, reason through the implications. So one implication is, let's say you fine-tune a model for summarization. Well, then in some sense, you've narrowed the model's distribution to, like summarization inputs and outputs. And so it won't necessarily work well on some other task like translation. Whereas a general pre-trained model, the same model could work well on multiple tasks. Similarly, if you have like specific formatting in your fine-tuning, Well, then now the model has been like fit to this particular distribution that has the formatting. And so if you change the formatting, then the model might not work well. So like in the fine tuning example we saw, I formatted all the examples with this like very specific format, like beginning of sentence, name, end of sentence. And if you kind of change that at when you're generating, um, it'll be kind of out of distribution and might not work well. Also, if you fine tune a model, then it's not necessarily guaranteed that it retains the ability to do this few shot learning. Because again, you might be fine tuning it on these specific input and output examples, and the model can kind of forget the few shot learning capability that the pre-trained model has. So yeah, any questions on this? Okay. So that's it for the fine-tuning basics. And now I'm going to go to instruction tuning. And so this is something that is incredibly popular now. And most language models that you'll use nowadays will have a base version, which is the fine-tuned model. Sorry, the pre-trained model. And then they'll have an instruction-tuned version that has undergone this instruction tuning procedure. So here the basic idea is kind of to use this observation or this kind of trick, which is we want to fine tune a model to perform multiple tasks. And the insight is that many tasks in natural language processing can be formulated as follows. We have some instruction that describes what the task is. Then we give a model an input from the task and an output from the task. So an example is here we could view this as an instruction, and it's basically describing the task. It's saying that this task is translation into English, and then we give it an input in Japanese, and then it knows what task to perform and gives a translation. And so then the insight is that you don't have to just train a model for one task at a time. You could just have an entire data set of these different instructions and multiple tasks and just fine tune a model on a data set that looks like this. So that's really the key idea behind what is called instruction tuning. And there's been, hundreds, maybe thousands of papers about this. So there's a lot of different variations that people have tried. So one question is, where do you get your instructions from? So I'll show a few examples. We'll see an example where you kind of have a hard-coded template to produce the instruction. You could, of course, have human labelers, like create these instructions. You could even have models generate the instructions, and I'll show you an example of that. And then similarly, you could determine where do you get your inputs and where do you get your outputs from. So we'll see an example next where you just take an existing data set, like a translation data set, and just put it into this instruction tuning format. You could again have humans specifically write, inputs, or have models generate them. And so we'll see an example of some of these combinations. And then another big thing is people try to develop these instruction tuning data sets for particular domains. So one is you might want some just general data set that tries to cover all the tasks possible. Or you might think about like, okay, for just code tasks, let's come up with an instruction tuning data set. Or for just math tasks, or one that we'll go into in a bit more detail is if you want to build a kind of good chatbot. Mhm.
I have a random question, but is this kind of like how people turn, like, for example, chatbots into like agents? Where like you have a regularized chatbot, but then you turn it to like the agent or like a specific chatbot for like the website, for example? Is this what this is similar to doing, or is this like completely different?
So yeah, that's a good question. So we'll go over we have a separate lecture on agents. And there's different definitions of agents. But yeah, usually you start, so with a language model agent, you start with a model that has been uh, general instruction tuned. So it can take like different instructions. And then you might have different prompts that say like, okay, given this HTML page, like determine what I should do next or something. And then it says what it should do next. So in some sense, it's following an instruction which says like choose an action for what to do next. And then there's some other extra things that what people typically call agents have. They usually have some kind of environment where they can make these like tool calls. Like they might have a browser available to them and they can like call a web browser and things like that. But yeah, at its core, you'll start with one of these kind of general purpose language models. Okay, so yeah, let's take a look at these, and part of it is a kind of history lesson too. So the first two examples are, uh, m- yeah, maybe two of the initial instruction tuning papers, at least the ones that kind of got very popular. So this one was from Google, and here they started out with 62 different NLP data sets. And I guess at the time, a large portion of the community would kind of work on one data set at a time. So they took all of the data sets available in NLP and then formatted it in as an instruction following data set. So for example, here's like a common sense reasoning data set. On the right here is a translation data set. They have sentiment analysis, co-reference resolution, and so on. And then for each different data set, they manually wrote some number of different templates that created an instruction. So here is, again, these are like task specific, but for this task, they came up with like four different ways of kind of having an instruction for the task. And then again, their inputs and their outputs are just taken from the data sets. Um, so yeah, this was the basic idea behind this method called FLAN. I forgot what it stands for, but maybe someone can look it up. And really the key finding of these early papers was that if you do the instruction tuning, the model can usually perform better than if you just fine tune on one task. So there's some transfer between the tasks. But very importantly, it can actually solve tasks that weren't in its training data. So here, what they did is they held out some tasks and then tested the model on one of these held out tasks. And you could see that their model actually did better than these kind of state-of-the-art, just pre-trained models that were using the few shot prompting. And you could kind of demonstrate this ability to generalize to unseen tasks using different kinds of plots. This is just one of them. But that was kind of the key finding. One, that you could have a single model that performs multiple, and it could even perform tasks that weren't in its training data. So then, yeah, here's some other cases. So this is a data set called supernatural instructions. And the original data set was called natural instructions. And I just wanted to call it out because natural instructions was from this paper by Swaroop Mishra. And this one was actually from like 6 months before the Google paper that got really famous. So it is kind of cool to look back and try to see like what were the really early papers. But anyways, they later scaled up natural instructions and this time they had humans come up with many different like task examples. So basically they came up with these higher level task categories. And then I think they did it through GitHub where like anyone could contribute. And they had something like 88 contributors and came up with oh, I forgot to put the number here, but came up with this huge instruction tuning data set that was just created by different people. So then another interesting finding was that you don't necessarily have to have humans create the instructions, the instruction tuning data. You can also just have really good language models create it. So this was one of the, oh, sorry, I forgot to update this. Um, but the link is on the course page. So this is a paper called Self-Instruct. And the idea here is you start with some small seed data set. I think they used 175 examples. Then you could use these examples to prompt a language model and just have it generate new data. And then they have a few other steps after, like they try to filter it down and various things. And you could imagine that since this paper, there's been, many different people looking into different techniques. But the core kind of idea is that at some point they have a language model that is just generating new data. And then, of course, you can iterate the procedure where you use this generated data to reprompt the model, and you can kind of balance out the data set to make sure, um, you have a good balance of different kinds. So the key benefit here is that now you're not bottlenecked by the human ability to create instructions. So part of it was showing that you can scale up to this kind of large instruction tuning data set. And so here's some examples that were generated. Like this one is given an address and city, come up with the zip code. It gives some address and city and then has a zip code. This one's kind of interesting. You can have, tasks that um, don't like it's hard to distinguish between what's the instruction or what's the input. So it just leaves the input empty and then says to generate some code. Um, can anyone think of some potential limitation with this paradigm? Well, one question I have is like, is this the actual zip code for San Francisco? Mhm.
This is any biases are going to explode as you repeat self-instruction because
Mm.
they don't have any alternate point of truth.
Yeah.
Second of all, there is like minute errors might creep in at some points and they will amplify each other out. Like that's one thing.
Mhm.
And last time I was thinking about like the probability distribution because you're gonna be getting out if I have like a quality metric and I have like a probability distribution. So like some examples are really high quality, like you could consider like a PhD wrote those examples. And a few other ones are really low output qualities, like probably even a grade school wouldn't give those outputs. So possibility is that like if one end of this probability spectrum dominates, like I have more grade school level outputs than PhD outputs in the self-instruct data set, that can lead towards like a large scale worsening of net output as I sort of fine tune upon increasingly worse examples. That's those three things.
Yeah, yeah. Yeah, so one, you could have this. Well, so part of it is, yeah, ultimately using a language model. And so one is the language model might be imperfect. So one thing is we don't necessarily know whether the outputs are correct or not. Like it might have just invented this zip code here. And then if you were to feed this back into the prompt, then it might have some kind of amplifying behavior. So you really have to be careful about having some way of you have to either just trust the language model or you have to add in some, filtering step if you really care about having, correct and high quality outputs. Um, so that's really it in terms of the key idea behind instruction tuning. So
The difference between instruction tuning and the fine tuning we saw at the start is that these fine tuned models have a broader range of capabilities.
yeah, so yeah, I guess fine tuning maybe you could view it as it's just like the procedure of minimizing a loss function with some data set and some model. And then instruction tuning would be a particular type of fine tuning where you format the data in this way. And yeah, the finding is that if you format it in this way, then you can get a model that kind of performs well in multiple tasks.
Theoretically, like, what's the difference between um pre-training and simply having like a really, really good initialization?
Um, so ultimately, I mean, one way to look at it is you could look at the code, and the code is just initializing the model, and the model is some set of parameters. So pre-training ultimately is just choosing some initialization.
Like, question, I guess my follow-up question is so the fine-tuning paradigm is about taking this just like sort of narrowing the distribution per se. So I'm curious about like have any experiments been conducted wherein like you train on a small specialized data set and then you allow it to explode the probability distribution by general retraining, and then once again you try to narrow the example down by fine-tuning in another data set? Like have experiments like this been conducted? Because
So you mean do like pre-train, fine-tune, pre-train?
sort of so like fine-tune-esque, pre-train-esque fine-tune.
Hmm. Yeah, I'm not aware of that specific order. Um, I would say that people kind of use this intuition of narrowing the distribution in one other way, which is typically nowadays the pre-training will be done in multiple phases. So the first phase will just be on general data from the web. And then towards the end of pre-training, they'll actually put in some task-specific data, or they'll use really high-quality filtering so that the model starts kind of narrowing its distribution to a higher quality area. And then they'll finally do the instruction tuning. Um, so it's not exactly what you asked, but yeah, maybe it's an example where you kind of use this intuition. Mhm.
So, the chat language models with which we interact are trained this way?
Yeah, so we'll get to chat. So chat is yeah, we'll talk about chat in a second. Mhm. Uh, yes, yeah, yeah. And then I'll talk about chat in a second. With chat, the distinction between an instruction and input kind of gets blurred. It's just like an input prompt, but yeah. Mhm.
Based on the example, using instruction tuning, we cannot verify the accuracy, but for current LLM, it's not the case. Like some of them have that kind of accuracy. So is it because of the data or the way it is pre-trained and like instruction tuned or fine-tuned?
Yeah, um so ultimately it's important to evaluate the model on some kind of third-party evaluation data that's really high quality. And so then even if your instruction tuning data is kind of noisy and has errors in it, then people will say, oh, well, at the end of the day, it actually performs well on these evaluation tasks. In practice, I would say that it's still important to have very high quality instruction data. So if you look at the Llama 3 paper, for example, they mention that they hire human annotators to create, a large portion of their instruction tuning data. That's likely because they did a bunch of experiments and found that, still having the high quality, um, yeah, data can have an impact. Okay, so yeah, so I wanted to specifically mention chat. So this is a term I just came up with while creating the lecture, but there is a slight difference between the fine tuning that you do for chat and instruction tuning, but people still refer to this as instruction tuning. But I want to just like show you what the differences are. So again, ultimately, when we have a chat model, we format the chat as a sequence of tokens. So in lecture 8, we talked about this, where you have this system prompt, and then you have this alternating conversation between some user and some assistant. So there's a couple differences. One is now you have this system prompt. That wasn't necessarily in the instruction tuning data sets. The other is that now you have multiple turns. So most of these instruction tuning data sets are, just some single input and some output. Um, and then the third thing is that if you think about having a conversation with like ChatGPT, then you don't necessarily say, okay, here's my instruction, here's the input. You kind of just say like, do this, and somewhere in there is the input and the instruction. Um, so yeah, the first difference was the system prompts. And so if we look at data sets that were created to fine tune some of the chat models, some of them specifically think about, creating the system prompts. Here's one I mentioned from before. And what they did here is pretty simple. They just wrote 16 different system prompts. You could see like they vary a bit. And then they append the kind of instruction tuning data. Um, so, and then here, here they also use the idea of just getting outputs from a model. So, yeah, given this, they would just pass it to GPT-4 and do this. And now they have this massive data set. If we look at the Llama 3 paper, so first of all, they don't mention all of the details, but they do mention system prompts a lot. So you can imagine that as they're designing their model, yeah, this is something they're thinking about. One thing they did mention is they did hire humans in some cases to write the system prompts. And you can see that these are a bit more sophisticated than the ones on the previous slide. And then this is something we'll talk about when we talk about the agents. But agents will typically have access to different tools. And so they also specifically put information in the system prompt for like what tools or what environments the language model has access to. And you could imagine that like the model might solve a problem differently if it knows it has access to Wolfram Alpha versus if that wasn't in the system prompt. So then the other difference is again the multi-turn nature, and also just having kind of natural conversations. So there's been a couple efforts to collect these multi-turn conversations. I think one of the earliest ones was this one called LMSys 1 million. And so basically, one of the early models that was trained, I think by Stanford, they put it up on some public service and said, check the box if it's okay if we save the, the conversations. And they collected a 1 million examples of actual chats. And you can see up here is this category called turn, and it goes from 1 to 22. Most of them turn out to be fairly short. I think on average, the length is 2. Um, or maybe this is the length. Yeah, sorry, yeah. Anyways. But you could see here that they do have these multi-turn conversations, and they're not necessarily formatted into this kind of strict instruction input format. Okay, so nowadays you might use data like this and add in the system prompts and then turn them into um, a kind of sequence of tokens and then fine tune your model on it, and you can get some basic chatbot. So any questions here? Mhm. Mhm. Yeah. Yeah, that's a good question. I don't know if I have a good answer. I would say the more you have, the better, because then it's kind of learning the distribution of different system prompts. So I don't know if they put the exact number in the Llama paper, but just the number of times that they mention the system prompt, you can tell that it's something, that they were thinking about a lot. And so they were probably trying a lot of different system prompts and putting them into the data. Um, there might be papers that have looked into that. I would have to look after the lecture though. Mhm.
Can system prompts be used for instruction tuning in general? Like why specifically use them for only chat tuning?
Yeah, so I guess it's kind of just the way that the I guess it's since you have multiple turns in a conversation, the point of the sensitive prompt is to have something that stays the same across multiple turns. So yeah. Mhm.
Start building context learning and then find, but like how you make that decision. Because now we have models with pretty big context size. I think for AI has around 100,000 tokens.
Mhm.
When you make that decision, or is that even the order?
Yeah, that's a good question. So the question is, let's say we care about a specific task. Kind of should we use in context learning, few shot learning, or fine tuning? And when do you decide? How do you decide? I would say, yeah, first of all, one determiner is the amount of data you have for the task. So if you have a very small amount of data, then you might just be limited to prompting or few shot learning. If you have a large amount of data, I would say it's less common to prompt a model with a lot of data, but people are starting to explore that. And yeah, now that we have really long context models, you can do that. So I would say some of it depends on like if you're able to fine tune the model and are fine with having a separate copy of the model for your task, then in general, fine tuning is adjusting, billions of parameters in the model. So it should be better than prompting if you have enough data. But sometimes people will just prompt because they don't want to go through the trouble of fine tuning. Okay. So next I wanted to mention this idea of knowledge distillation. So several methods that we discussed use a model to generate data for another model. Um, and the kind of framework for this is that doing this is an instance of what's called knowledge distillation, where we have some teacher model, and it could be a larger model like, GPT-4 or, better model. And then we're in some sense distilling information from it into a student model, which could be something like a small language model. And so there's two different ways to do distillation. Um, the first way, and this was like the traditional way where it was proposed, is you train the student to literally mimic the next token distributions from the teacher. So for example, here we have translation, or this could be an instruction and an output. And then we get some next token distributions. And then we take the cross entropy between uh, these two distributions. So the idea is that the student is basically fitting its distribution to the teacher's next token distribution. And so you could see here, this is just the cross entropy loss that we've seen before. But now you have some supervision on basically like every possible next token. So this was proposed in 2015 in the context of image classification, I believe. But some people do use this with language models. Like one of the models trained by Google called Gemma actually used this kind of token level distillation to train a smaller model using knowledge from a larger one. Um, Maybe I'll skip this or just mention it briefly, but again, there's this connection between cross entropy loss and KL divergence. And so the way you can think of this is that the student is learning the distribution of the teacher, and you can show that this is the case. Um, uh, yeah, using a similar derivation from lecture 3. Um, But yeah, I wanted to mention this one, which is called sequence level knowledge distillation. And so this looks a lot like what we talk about when we like generate a data set with a model, say GPT-4. So here we're not looking at next token distributions. We just generate some full sequences with the teacher model. And then the student model fine tunes or trains on the resulting data set, right? So we have this now data set of like prompts and responses, and we can fine tune the student model on it. So it turns out that this is actually, so here's an example, a real world example. So recently there's this DeepSeek model, DeepSeek R1, and they created these smaller models, which were distilled versions. And so if you look at the name of the model, it might be something like DeepSeek R1 Distill Quen 7B. And that means that their student model is just 7 billion parameters. And it's basically just trained on, outputs that were produced by the larger DeepSeek model. And so I wanted to be sure to tell you about this because, yeah, you'll definitely see this term distillation come up. And it actually relates to this idea of fine-tuning a model on kind of synthesized data from some teacher model. The interesting thing here is that this also minimizes the KL divergence between the teacher and the student. So the student, yeah, is essentially learning to mimic this larger model or the teacher model. You could again like write out the definition of KL divergence and you eventually get something like this. And so now you can see that we don't have this supervision at the next token level. It's just taking this kind of sequence sample from the teacher and then minimizing the negative log probability or maximizing the probability of the sequence.
How do you implement something like this? Like, what are the algorithms to fit the students' distribution to the teachers?
Yeah, so this is it's just what we've been talking about. So you basically generate the data and then you fine-tune the model to predict the next token in the response given the prompt.
Does that make the students' weights approximate the teachers? Just from fine-tuning on the teachers generated data?
Yeah. So I'm going through this kind of quick, but basically when you do the next token prediction, you are maximizing the likelihood or you're minimizing this minus log probability of the sequence. And so then this slide is just saying that, yeah, doing that procedure, basically, generating a data set and then training the student model on it actually corresponds to the student fitting the teacher's distribution over outputs.
Is there any other advantage of doing this other than ending up with a smaller model that's like easier to carry around?
Yeah, so another another potential benefit is that well, yeah, so a main benefit is you can get a smaller model. Another is that you could imagine um the teacher model. Yeah, sorry, I'm going through this kind of fast. The teacher model you can kind of augment with other stuff. So for example, you could sample from the teacher, and let's say you have some verifier that, checks whether the solutions are correct or not. Then you can filter out the incorrect ones and only train on the correct ones. And so now you're actually training on something slightly different from the teacher distribution. It's the teacher distribution, but only restricted to like the correct outputs. And so in this sense, you could in theory even do a bit better than the teacher because your distribution's been kind of filtered. Yeah. Okay, and so then let me just briefly go through the efficient fine tuning. And I should mention that the author of one of the techniques will be giving a guest lecture on quantization. So I think during that lecture, he'll go into more detail on this. So the idea is that, one option is to fine tune your model and update all of its parameters. Um, but this can get pretty expensive. So let's say we're trying to fine tune a 65 billion parameter model. Then each parameter, let's say that it's represented using 16-bit precision, then the parameters will be 130 gigabytes that you would need to put into GPU memory. You also need to take the gradients when you're optimizing. So that'll be another 130 gigabytes. And then if you're using an optimizer like Atom, if you remember, it kept track of these different statistics, like the first order statistics and second order. Usually those are actually stored in like 32-bit precision. Again, Tim Detmers is giving the guest lecture on quantization, and he'll talk about this idea of precision in a lot more detail, so I'm just going through it kind of quickly now. But this is just getting across the message that, if you want to fine tune a large model, it requires a lot of memory. And so if we look at some example GPUs, then yeah, here we typically have a GPU that's like 24 gigabytes or maybe up to 80 gigabytes. And so we have to do something, because back on that previous slide, we had like hundreds of gigabytes or thousands. So one option is to split up the model across, multiple GPUs. We'll actually talk about that in a later lecture as well, like parallelization techniques. But what you could do is you could try to get clever and only update part of your model. So instead of updating all of the model's parameters, just update a smaller number of parameters. So one of the most common ways nowadays for doing this is called LoRa, or low rank adaptation. So for example, if you look at those two fine-tuning libraries I mentioned, then they'll definitely have LoRa implemented. So you'll see this term come up a lot. And the idea here is here's the kind of key picture. So here in your transformer, let's just consider one weight matrix. So this could be the weights in the attention layer, for example. The key idea behind LoRa is to not update these weights, but instead just introduce the small number of weights here. And the weights are basically find the difference between the pre-trained weights and the kind of new fine-tuned weights. Okay, so now again, you're not fine-tuning the original weights, you're just finding the difference. And then the other key idea is you can reduce the number of these parameters by making it low rank. So here we're like reducing the size of this inner dimension. And here the hypothesis, and they talk about this like in the paper, is that, after the model's been pre-trained, maybe you actually only need kind of a, small dimensional subspace to update the model to a good point. Okay, so now what you do is just introduce these LoRa layers for like different parts of the network, and you freeze all of the model's parameters and only update these. So now the cool thing is that if you look at this equation, then you have your original weights and you have the new ones that you're actually updating, and they're just added together. So then what you can do is after you do the fine tuning, you can literally just like add these to the weights of the network and then save the model and use it and deploy it. So there's actually nothing extra that you have to add on to the model. You're, again, just learning these numbers that you then add to the original weights. So this is like really widely used now. Again, if you look at the number of parameters in these orange parts, it's much, much smaller than the number of parameters in the full model. And it's very convenient because after you fine tune, you can just add the numbers into the existing weights.
If we were doing this, we have to know memory of the pre-trained weights and the new matrix of differences, giving us an overall higher memory consumption.
Yeah, so the one key difference is that you're not computing the gradients for the weights. So you're not computing the gradients, and then if you're like using Atom, you're not keeping track of those statistics. Yeah. Mhm.
Matrix is visualized.
Yeah, they in the paper they just say they do that so that it starts at zero. Um, there might be a deeper reason, but oh yeah, I'm not aware of it. Mhm.
Substitute for time, it's in a very like memory efficient way. Really cool.
Yeah. So the idea is your fine-tuning code stays exactly the same from, aside like inside your model, you have to implement these little LoRa layers. But then the fine-tuning code stays the same. You just freeze your model parameter weights, and you're fine-tuning and only updating the weights in orange.
So it's still fine.
Mhm. Yeah. Yeah, it's fine-tuning, but you're only adjusting parameters for these LoRa layers. You're not updating all of the parameters of the model. Yeah, so you still have to do the forward pass through the entire model. And then the key difference is that you're only taking gradients for these kind of small orange weights, and it becomes a lot more efficient. Yeah.
Is versus a model that's actually fine-tuned with like,
Mhm.
by using normal memory and computation.
Yeah.
Do you think there's like a performance difference?
Yeah. Yeah, so that's a really great question. I don't have like an all-encompassing definitive answer, but one way to think about it is that if you update all of the model's weights, then you kind of have more degrees of freedom. So you have billions of parameters that could be adjusted. Whereas with LoRa, you have a smaller number of parameters. Um, so roughly speaking, for some tasks, you'll be able to match the performance with LoRa. I think roughly speaking, like if you're doing classification or something like that, but then if you're doing a really long, like complex long form generation, then people will start to see performance gaps because maybe you actually have to update, larger parts of the model. Yeah. Okay, and then let me just mention this quickly, but as I mentioned, the author will be giving a guest lecture about this. But there's an even more efficient version called QLoRa. And the idea here is you can do what's called quantize the model. So instead of representing the model as 16 bits, you can represent it as 4 bits. Um, However, they keep the LoRa adapters at 16 bits, and they come up with ways of like offloading computations to the CPU and things like that. Um, so again, I want just in case you see this QLoRa, it's also implemented in all the libraries now. And in practice, it can let you like fine tune really large models on like one GPU and things like that. Um, but as I mentioned, Tim will give a whole lecture on quantization, and we'll go into this in more detail. Okay, cool. So we have um, like 2 minutes. I wanted to just give this recap and maybe introduce a couple more like summary insights. So again, with fine tuning, we're ultimately adjusting a model's parameters using some data. And then instruction tuning, you can kind of think as a clever way of formatting the data so that the model can learn to do multiple tasks. And then knowledge distillation, I went through it kind of quickly, but one insight is that the data can come from various teachers, and ultimately we're fitting the model distribution to kind of match the teacher distribution. So you can even think of like fine tuning as being this data set that's kind of produced by maybe a human. But you can also have models kind of generate the data that you fine tune on. And then you can do this more efficiently by only updating some of the model's parameters. So that's it for today.